Hello, class. Welcome to the online session of statics course. So we're in the chapter 11, and in the class, I have covered some of the slides already, but I'll give you a quick overview of our discussion. So we studied equilibrium of rigid body and our ability to draw free body diagrams. So if you remember, before the spring break, we covered almost up to this concept. So our primary objective in this course is to enable our ability to represent supports with their support reactions and representing supports with proper support reactions in the free body diagrams. This is the These are the two important objectives of this chapter. So in the picture that's shown here, there are two smooth pipes. There's a pipe A, pipe B. And if you remember, I asked you to draw a free body diagram of two pipes as a single entity, which is given on the right here. There's a pipe A, pipe B. But we can also draw two separate free body diagrams for the pipe A and pipe B. So if we were to do that, we will see something like this. You can see at the screen on the right, which is the scratch base. For example, you can have a pipe A. So if you only treat pipe A, we have a smooth contact here. We can express that as F, and a smooth contact here. We can express that as T. Then we have a contact due to the pipe B, and due to that contact, we should give a reaction due to B. That's how the free body diagram of the pipe would be. Obviously, we should also draw the weight, whatever is the weight, W. In addition to this, remember when we draw the free body diagrams, we have to assume proper axis. So we give this to be our x-axis and that one to be our y, because majority of forces are aligned along x and y. So the t is on positive x, rb is along negative x, f is along positive y, and w is the only force which is not along x or y, it's between them. Hence we have to give angles, especially for w with respect to either x or with respect to y. So if you remember the statement I provided in class, if an inclined plane makes an angle theta with the horizontal, and in the picture given, this t, assuming t is the inclined plane, it is making an angle 30 with the horizontal, then normal to the inclined plane, which is the f, makes the same angle, normal to the inclined plane makes the same angle with vertical. That means this will become 30 degrees. So this can be treated as a free body diagram of A. Similarly, we can draw a free body diagram of B. Everything remains the same except that for B, you have, that is B, because RB is acting on A, we have to draw equal and opposite RB. And there is the weight, obviously, W, let's treat it as W2. and there is a force P. Again, axes are X and Y. So we have to give the angle made by W with respect to P, and that would be again 30 degrees. And that is a free body diagram of B. Now this is the example I gave you if we were treating A and B to be separate entities. But if we treat A and B to be a single entity, that means we're not separating them, and that's what is shown here when both are treated as treated as single entities. So coming back to the concept, here we are trying to enable our ability to draw free body diagrams by having proper assumptions for the supports. Here, in the example that we just saw here, the support is provided by the fork attachment. So we remove the fork. So this is the fork. We remove this. And due to this removal, we have to express with proper reaction force. And the reaction forces are F, P, and T in this example. So we will see, for example, situations where, for example, in this situation, we'll see some situations where we should be able to express the supports with proper reaction forces. For example, here, so this is this one here. That's a pin joint, isn't it? There's a pin joint. So this platform is free to rotate with respect to this joint. Let's name it A. That's what is given here. And this is an example we already solved in class before the spring break. And we also have ropes. This is the rope. Rope is going from here all the way to that point. So we treat, and there are two ropes here, and an equivalent figure would be is given on the right here. But the free body diagram for that system is here. So try to understand the free body diagram. An important concept here is the pin joint at A is represented by two forces. And the reason is because at A, the pin joint prevents the platform to move in the X, to move in the Y. It prevents translation along X or translation along Y. But it allows free rotation. Hence, we don't have a moment reaction, but we have only the force reactions. Similarly, at B, we have rope. And remember, ropes, the way to represent ropes are always tension. Ropes can only withstand tension, not compression. They're not designed for that purpose. And we saw this example in class. We solved a problem on that. For example, if you see a system like this, so here you see there is a beam. It is fixed at A. It is not a pin joint at A. When it is fixed at A, that means a fixed support would prevent the beam from moving right, from going top and bottom. And not only that, it also prevents the beam from rotation. That means you should also give a couple moment like that. So it prevents motion in X. So we have Fx or Ax. It prevents translation along Y. So you have Ay. And it prevents rotation. So we should also represent that with moment at A. So that's why the free body diagram is given on the right. So you see, we gave the axis, our assumption. This is our x-axis, that is our y-axis. And we have AX, AY, moment at A. Now, the direction, we can assume any direction when we solve the problem. But if we get a negative answer, it means our assumed direction is opposite. That's it. So what we need to see is various support reactions. And how do we represent the support reactions is what we're supposed to see. For example, here, you see this is a roller on an inclined plane. That means what happens to a roller on an inclined plane? It is free to move along the inclined plane, but it is not free to move into the inclined plane. That is why you have a reaction force that is perpendicular to the surface of the inclined plane acting on this part. So the free body diagram would be, it's not a free body diagram. This is how we represent this support. This is how we represent this support with an equivalent force here. For example, look at this support pin joint. This is a pin at that point. For this pin, what we see is for the pin joint here, this rod is free to rotate, but it is not free to translate along x. So we have fx. It is not free to translate along y. So we have fy. So we give reaction forces when the support opposes certain motion along that axis. So it is free to rotate. Hence, we don't have a moment reaction because it is not free to translate along x. We have fx, not free. It is not free to translate along y, so we have fy. Look at this case here. In this case, it's a fixed support. That means it is not free to move along x, not free to move along y. So no, not free to move along x, not free to move along y. Also, it is not free to rotate, so we should also give a moment reaction. So this is a fixed support. This is a smooth pin support, or we can also treat it to be hinge support when we see a 3D problem. This is a roller support. So with this background, we should be able to apply our skills to a problem that is shown here. So in this problem, there's an operator applying a vertical force to the pedal, and there is a spring attachment here, and there is another rod or a short link attached at B. How do we draw a free body diagram for this situation here? So I have taken the system, so I'm assuming the force applied by our foot on the pedal to be some F. I have the free body diagram. I have the equivalent system here. So let's look at this equivalent system. So at A, what do we have at A? At A, we have pin, right? That means when we have pin, it is free to rotate with respect to A, but it is not free to rotate along X or Y axis. That means first of all, we should assume and write what is our X, what is our Y. What is our X and what is our Y? Now we have to, so if we were to draw the free body diagram, at A, we have AX, and I can assume this is our AY. AX, AY. I can assume AY going down or going up. So once we start solving, if we get a positive answer, our assumption is correct. If we get a negative answer, our assumption is opposite. So the spring, we replace the spring in the free body diagram with an equivalent force F due to spring. If you remember the spring concept, force given or applied by a spring is the spring constant times the change in length or elongation, and X can also be compression. Then the short link B, it can be treated as a rod, and this is given as force F. Okay, so this is how we draw the free body diagram. And the distances, of course, we should have the distances as given in the picture, and which is what is represented if you observe on the slide. So this is the free body diagram. You must understand how to draw the free body diagram. So the takeaway point from here is you represented pin with two reaction forces. Number one, you represented a spring with a reaction force. You represented a link with the force that was applied or was taken into the spring or into the link. So how to represent a link with its equivalent force, a spring with its equivalent force, a pin with its two reaction forces? That's what we should see in the free body diagram. So, for example, how about this case? And this is a common site, right? This is a common site in our Odessa Midland regions. So how do you see this? So there is a platform, unloaded platform, and platform has weight. One thing we have to remember. Then the platform, how is the platform suspended? Now it's in equilibrium, right? If you look at this, there is the weight of the platform, and where does the weight act? The center of gravity. Assume that this is the center of gravity, and this is how the weight of the platform is. But what prevents the platform to not fall down? So what is balancing the weight? Isn't there a joint here? And let's call this pin joint. There are two pin joints, pin joint there and pin joint here. And also there are two ropes, rope attached there and rope attached here. So we can treat this as a 3D problem or a 2D problem because of symmetry. What we can draw, the way we can draw this is we can treat this to be this is how we can draw the platform. This is where W is. Now the reactions here would be, let's say, like that, like this. Let's call it point A. So we have AX and AY, the weight of the platform. And remember, we have the support at this point, and we can replace the ropes with equivalent tensions. And because we have two ropes, we can say there are two tensions, 2T, so we can get what is tension in each rope. That means we should also say this as 2AX and 2AY because we have two pins there. So this is how it reduces to a 2D problem, and we obviously have to give the axis X, we have to give the axis Y, and we have to give the distances. So we have to give what is this distance, we should also give what is this distance, we should also give what is this angle, So all of this has to be, and what is this distance, by the way? So we should give all these dimensions if we have to solve the problem for the reaction forces or for the tension. Okay, then you see the free body diagram is given on the right. That's how we have to draw the free body diagram. Now, once we draw the free body diagram, what we do is we calculate the values of AX, AY, tension. So three unknowns can be solved. Okay, now comes a quick question for us here. So if we were to draw the free body diagram of the beam, okay, then how many unknowns are present in the system? There is a beam, there's a cable with frictionless pulley at D, and there is a support. Sorry, it's a cable support that's passing through the pulley D, and there's a weight acting at C, and the weight is 80 times 9.81. So here we already know that this is 80 times 9.81, and units are important, so it's Newton. And this is a single cable that is passing from B to E and passing through D. So this we can treat to be tension. This is tension because the same rope, I'm representing that with the same variable T. And at A, what do we have? It's a pin joint. So we have AX and we have AY. So each time we should not forget to give the axis. So that's the free body diagram. Now in this free body diagram, which is given here, it's given here in this free body diagram. Tell me how many unknowns are present. Number one, we have T. Number two, we have AX, AY. So we have three unknown forces. Are those forces or couple moments? Are those forces or moments? These are all forces, right? So that means we have three forces. So which option would you select? C, right? Okay. Then let's look at this problem here. Now you tell me how many, how many unknown reactions are present here? At A, we have a roller support that is in contact with a plane. That means how do we draw the reaction when we have to draw the free body diagram? Because there is no support in a free body diagram, we have to express support with respect to reaction forces. So we will not draw this ground here, but we will replace this ground with a reaction force that is perpendicular to the ground. And at B, we have Bx and we have By. So, how many unknown how many unknowns are present in the system? Number one, we don't know what is R, we don't know what is Bx, we don't know what is By. So there's three unknowns. But the question is, if you change the direction of the force, that means if you change the direction of 390 not acting like this, but we change the direction of 390 to be acting like that. And also if the couple moment is not counterclock, but it is clock like this, what happens? The beam will lift from A, isn't it? It'll lift off from A. The beam will lift off at B? No, the option B is not correct, only option A is correct. So for this free body diagram, we are missing axis. So we say this is our X, this is our Y. That means we have to give angle made by the normal with respect to vertical is 30, because angle made by an inclined plane with horizontal is 30. And that's it. So this is the free body diagram. So we have to give the axis, we have to give all the angles, distances that'll help us set up the problem and solve the problem. Now let's try to solve some problems here. So here, what's given here? Now, what are the reactions at A? What are the reactions at B? What is the reaction at C? And what are the values? How much are those? That's the question. So we have to first of all draw the free body diagram of the pipe. So to draw the free body diagram of the pipe, what should we do? We should first draw only the pipe. That means we will draw only the pipe. So I'm going to draw only the pipe. Then I will draw all the forces acting on the pipe. Number one is this 300 Newton, and it is acting at, this is 30 degrees. Then at C, now tell me what happens at C. This is C. The pipe cannot move vertically down, isn't it? If you only look at C, the motion of the pipe is restricted along this direction, but the pipe can move in any other direction. That means it can go up, it can move left, it can move right. That means if it's free to translate along certain direction, you will not have reaction force, but you'll have a reaction force only in that direction that prevents its motion. That means in this case, it's prevented to move in the negative y, so you have a reaction force at C. What happens at B? It can move up. What happens at A? So at A, the pipe can't move into the support. That means the reaction at A will be like that. That's the reaction at A. This is the reaction at B. So we have to assume some axis. This is our X, this is our Y. That means because reaction A is not along X or Y, so we have to give an angle. How do we give an angle?